Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Ramadana from Bilingual Education Study Program 2018. Today, I will explain about the Rutherford and Nielsberg atomic models. The aim of this explanation is to understand the student about the theory atomic model of Rutherford and Nielsberg. Around the year 1911, a British physicist, Ernest Rutherford, carried out the famous gold foil experiment. He did this to understand the structure of an atom. The experiment was carried out by Rutherford along with Hans Geiger and Ernest Marsden. The experiment he performed was a breakthrough in the field of chemistry, which helped him understand the structure of an atom in a more accurate manner. This is how the setup of his experiment looked like. As we can see here, he used source of alpha particles looped in a lead container with a very small slit. This ensured that the alpha particles only came out through a small opening and traveled in a straight line. But why did it select alpha particle in the first place? Well, the alpha particles were having high energy and were heavier as well. So, if we say the atom is like a pudding of positively charged particles with electron embedded in it, then the particle will pass right through it. This is obvious because the heavier particles will pierce through the lighter pudding structure and of the atom and pass through it. This is what Rutherford thought. For this reason, the greater mass and energy compared to the protons made him choose alpha particle for the experiment. Next, he used a very thin gold foil on which the alpha particle would bombard. Why did he choose a gold foil? Well, a really thin gold was estimated to contain approximately 1,000 atoms. Lesser than atoms, more confident the experiment will be. Lastly, we are able to look at this silver band with a gap here. What could this be? Well, this is a screen, a fluorescent screen that will help us to detect the radiation. That means the screen will glow or emit fluorescent light wherever alpha particle will hit it. So, this is how the track of alpha particles can be traced. Now we are all set to understand how the experiment works. The alpha particle will emit from the element present in this box. This directly hit the gold foil. Now, what should happen entirely? As we know, the Thomson model suggests that an atom is a sphere of positive charge with negative electron embedded inside it. That means it is expected that alpha particle will pass right through the atoms and hit the detector strike. And why so? Because the mass of alpha particles is heavier than mass of positive charge. That means they should directly hit the atom and move ahead. Only a very small deviation will probably be acceptable in this case. But is this what he observed? Not really. He was astonished to get an unexpected result. What result did he get? He found that most of the fast-moving alpha particles passed straight through the foil and hit the detector. However, some particles get deflected by small angles. And lastly, few alpha particles also rebound. Now, how can this be possible? These three observations made Rutherford think that the plum pudding model is not really correct. Rutherford's atomic model was quite commendable when it comes to explaining the structure of atoms. However, it was not very appropriate theoretically. And why are we saying so? We know that any charged object which revolves in a circular motion gains acceleration gradually. Similarly, if the electron is moving fast in a circular path, then it will also gain acceleration, and on gaining acceleration, it's bound to liberate energy in some form. Now, if it continuously keeps radiating off energy, then ultimately all the energy of the electron will get over and it will fall into the nucleus. This will result in high instability of the atom. But wait a second, all these things do not happen in an atom. And how we do know this? Because in the nature, all of the atoms are stable. That means the hypothesis put forth by Rutherford was also incorrect? Not really. The hypothesis just needs the slight modifications. These were made by the next legendary scientist in our list, called Niels Bohr. He made a few additional explanations to describe the atomic structure. The postulate put forward the Niels Bohr were as follows. Firstly, only certain special orbits called discrete orbits of electrons are allowed inside the atom. Secondly, while revolving in these discrete orbits, the electrons do not radiate energy. Now, this point definitely tells us why an atom is so stable. But what exactly are these paths? Are orbits in which the electron revolve around the nucleus. Let's understand with an example. Do you know how our solar system is? Yes, it appears somewhat like this. Now, where the sun is stationary at the center, while the planet revolve around it. But have you noticed that the planet always revolve in the fixed path? We never find any planet jumping to a different path all of a sudden, right? They always encircle the sun in defined paths. In a similar way, we have the atomic structure. The nucleus acts like the sun located at the center, and the electron like a planet which revolve in fixed, defined orbitals. These electron orbitals are referred to as cells or energy levels. Now, the name energy level gets us to an important concept. Niels Bohr suggests that the electrons revolving in these orbitals do not radiate energy. Now, this is just justified when we use the term energy levels, because it indicates that each cell has got a defined energy levels. That means when the electrons revolve in these cells, they do not liberate any form of energy. And how do we name these cells to indicate their positions? It's simple. Beginning from the one near the nucleus, we name them as the K cell, L cell, M cell, N cell, and so on. Yes, K, L, M, N, and so on. And what if we want to number them? In that case, we use the letter N in lowercase and write them as N equals 1, N equals 2, N equals 3, and so on. Beginning from the one next to the nucleus, so we can name them alphabetically or we can even number them. With all these theories and points known, do we know the structure of typical atom completely? The nucleus contains positive protons and the electrons, revolving around in the fixed orbitals. Is that how an atom is structured? Not really. We still have one more subatomic particle left. And what and where could it be? Let's find it out. It was around the year 1932 when a famous English physicist, Sir James Chadwick, found the third subatomic particles. He found that the particle had a mass almost equivalent to that of the proton. And what about the charge? Astonishingly, it had no charge. Yes, the particle is neutral. The particle was later named as neutron, denoted by letter N. Thus now we have the complete design of an atom.